Today's topic presenter is Colton Raffy, our senior SAS programmer. I'll go ahead and hand it off to him.
Thank you, Laura. Let me just share my screen and we'll just start from here. Can you see my screen here?
Yeah, we can see it.
Okay. So this topic, or office hours, is about working with data frames in Python. So if you're expecting another topic, sorry you got me in working with data frames in Python. A quick introduction on the topic here, kind of why do I need to learn this? Mastering data frame operations and understanding how code is executed in Databricks Python is crucial for optimizing performance and efficiently working with large data frames and ensuring accurate results. Before I start, let me see if I can get the note. Let me put the notebook in here. So I just shared the notebook if you guys want to kind of follow along. Some of the knowledge goals for this session: you'll understand the advantages and limitations of each type of data frame in terms of performance, scalability, and use cases. You'll grasp the concepts of eager and lazy execution and kind of what data frames use either of them, and then kind of how they impact data processing and performance. You'll comprehend the different stages of the execution or of Spark's execution plan, from job submission to the test execution. And then we'll finish off, you'll learn how to manipulate, group, and join PySpark, Pandas, or Pandas data frames in Python. The topic outline kind of goes along with the knowledge goals. We'll start off with the overview of the data frames, talk a little bit about eager and lazy execution, go further into lazy execution with the execution plan, and then we'll finish off by talking about the common transformations. I'll stop for questions after the second, third, and then after I'm done for questions. And you guys can put the questions in the chat, and my team will answer them, or I can answer them verbally if they don't get to them. So starting out with an overview of the data frames in Python. So the PySpark, an overview of the PySpark data frame. It's distributed data structure optimized for large-scale data processing via Apache Spark. It operates across the distributed cluster, leveraging that driver node, which is going to coordinate the task. And then those worker nodes are going to execute that task in parallel. It uses a lazy execution in the execution plan to optimize the performance. It can read and write directly from and to CDR database tables, as well as the distributed storage, such as the Databricks file system, or S3, which is the SAS workbench. It's going to be the fastest of the three data frames we talk about today. For the large-scale data processing due to the distributed computing power. Next, we got the PySpark Pandas data frame. It's an extension of the PySpark data frame that offers a more familiar Pandas-like API, allowing users to operate on that PySpark data frame using that Pandas-like syntax. It is a PySpark data frame, so it's going to be that distributed data structure operating on that distributed cluster using that lazy execution and then that execution plan. For the speed on the PySpark Pandas, it's going to be pretty fast because it uses that Spark's distributed capabilities. However, it has some overhead introduced due to that Pandas-like API, which is going to make it slightly slower than PySpark for them large-scale data processing. Next, we got the Pandas data frame, and kind of people coming into Python are probably familiar with the Pandas data frame. It's a non-distributed in-memory data structure for Python. It operates on that single driver node. It uses eager execution. And like I said before, we'll talk more about the eager execution and then the lazy execution. They cannot directly read or write to CDR database tables or distributed storage. Instead, data must be read into memory after being moved to that local storage or written back to local storage and moved to S3. And there are plenty of examples of writing and moving Pandas data frames and that kind of thing from the introduction to Python in the data camp section. In terms of performance for Pandas compared to the other three, it's going to be slowest for the large scale data processing due to the single node, due to the processing on that single node and processing that occurs. So kind of the main takeaway that I want you guys to take away from this graph or this chart, kind of use the PySpark data frames where you can, kind of as often as you can, due to the performance and the speed of the PySpark data frame. Kind of moving along to how the data frames are executed, eager versus lazy. So I'm going to start off talking the eager execution. So Pandas data frames use eager execution. Eager execution refers to the immediate execution of the operations. So when you perform an operation on a Pandas data frame, the operation is immediately executed and the results are stored in memory. Let's take a look at a quick example of how this occurs. So this example creates a Pandas data frame, filters out the younger people in it, and then displays the results. And for a Pandas data frame, each step is going to be executed immediately. The Pandas data frame is going to be created and available in memory right away before this next step occurs. And these steps are going to happen immediately and then in sequence. It's not waiting for, say, the display rows or an action to create a plan like we'll talk about in a little bit with the lazy execution. Kind of some benefits of the Pandas data frame and kind of the eager execution. It's going to be very straightforward and easy to understand. It's very easy to bug because the operations are run in sequence and run immediately. You get that immediate feedback. So like I said before, you're going to see those results right away. It's very intuitive, and you would think kind of all languages are like this. And SAS does, for them in general, run on eager execution. So that's kind of what you guys are familiar with. A couple of the drawbacks of eager execution using that Pandas data frame is it's not going to be suitable for the large data sets that can't fit in memory. There's no optimization for eager execution. Like I said before, it's going to run every operation kind of as it is, as it's programmed. Kind of moving on to the lazy execution. So this is what PySpark and PySpark Pandas data frames use. The lazy execution means the operations are not immediately executed. Instead, the computation is deferred until the results are actually needed, optimizing that performance by allowing the framework to create a plan and optimize those sequence of operations. Kind of in the PySpark code, deferring computation appears as defining transformations on the data without executing them immediately, those computations are postponed until an action like display a write is invoked to fetch these results. So let's take a look at the same example that we just looked at with a PySpark data frame, instead of a Pandas data frame. So the first two steps, the PySpark data frame step, and then the transformation of filtering rows, that's going to be recorded into the execution plan, but the computation is not going to happen yet. The computation is going to happen after this display statement, which then triggers the recorded transformations. So that's kind of the difference between the two. So the lazy execution is going to build a plan and kind of delay the execution until action sets it off. And then the eager is going to be straightforward, kind of what you see is what you get. Some benefits of the lazy. So you're going to have that improved execution speed, because the plan's going to be, the execution plan's going to be optimized. You're not going to use as many resources because it's going to get rid of any of the unnecessary things in your code, the operations. And it's going to be very good for handling some of those large data sets. One of the drawbacks, and I think one of the biggest things that's kind of hard to kind of catch on as you're working with PySpark data frames, is kind of the delayed error detection. And why it's delayed is because obviously when the plan is going to record the transformation steps, but it's not going to record, or it's not going to actually run the code until that display statement there in this example. But I think this is kind of hard to kind of catch on and get used to it, because when you see the code running one of your transformations, you think, oh, it's actually ran and computed that, but it's kind of waiting for that action to actually run that those recorded transformations. And then another drawback of the lazy execution is it's complex and it's hard to understand the execution plan, especially for beginners, because it's not going to be that kind of how you see it in the code is not necessarily how it's actually going to be ran there. I'm going to stop for questions. Are there any questions so far? Doesn't look like
We're not seeing any.
Okay. I'm going to move on to kind of digging deeper into the lazy execution. So the lazy execution in Spark involves using that execution plan like I talked about before. The execution plan optimizes how data transformations are processed and specified, kind of how those operations will be performed across the cluster. So I made this little diagram here that kind of shows how, or kind of the different steps of the execution plan from the job submission to the task execution. So the execution plan is going to start when that Spark action is called and triggers the submission of the job. After submitting the job, Spark parses the code and checks the syntax before generating an initial logical plan based on the data frame operations. Think of the initial logical plan as like a blueprint that kind of shows the different steps of what needs to be done with the data. Next, Spark generates an analyzed logical plan by validating that previous logical plan. This plan resolves columns and table names against the schema It checks whether the operations requested are feasible given the data types and schema. So kind of by this part, it ensures that the query is semantically accurate and ready for execution. Kind of the next part here is going to be kind of the optimization of the logical plan. So the Catalyst optimizer is going to apply the optimization rules to refine the analyzed logical plan, identifying and eliminating unnecessary computations. It then restructures the operation to maximize efficiency. Spark converts that optimized logical plan that was just created into a physical plan. This physical plan specifies the actual execution strategy, detailing how the different operations will be carried out on the cluster. Finally, Spark breaks down the physical plan into stages and tasks, and those tasks are distributed across the cluster for parallel processing. So this is kind of, I wouldn't get too in the weeds about this, but just kind of realize that the plan is to optimize, the execution plan is there to optimize the different data transformations and kind of specifies kind of how the different operations will run on the cluster. And like I said before, the major optimization is going to happen in this optimized logical plan with the Catalyst optimizer. And we're not going to go too deep into that today. But if you want to learn more kind of about how the plan is really optimized within that Catalyst optimizer, you can visit this blog, and I can put it in the chat here. Okay, so the next step here we're going to talk about is accessing the execution plans in PySpark. So this example is just another play example, I guess. It creates a data frame. It applies these two transformations, a select statement, a filter statement again, and then it applies an action. This displays the data frame. This comment's not accurate. The way to get the execution plan in PySpark is to use this .explain option. And the kind of the default is going to be, the default of the .explain option is going to be just to see this physical plan. I actually like to use this explain method with the mode extended, and that kind of shows you all the way from the initial logical plan down to the actual physical plan. Let me see if I can do this. Okay, so we're going to look at a little side by side of the results with the code to kind of see how it's going, kind of how it's processing through the different stages that we talked about before. So this physical plan output you see is from this initial explain statement there. Let's go down a little bit. So this extended is going to show those 4 steps I just talked about above. So the parse logical plan is going to show basically these operations kind of in the plan stage, or with this first one being you're reading in the ID and the name and the age and kind of creating that data set there. This project operation is going to be, you're going to be selecting the two variables. And then the filter is going to be this second transformation. So this kind of shows, it takes the code and puts it in that logical plan. This next step, you see in the analyze logical plan, you see the different variable types, and the names have been resolved. You see the filter statements actually been resolved in the literal, the 30 has been cast to a big int, so it can be compared against the age there. And then after that, it's going to be ready to execute. And then the optimized logical plan portion is going to optimize the different sequence of events here. We see the start is still the same with the ID, the name, and the age reading it in. You see this, the filter portion has actually changed to the first transformation after reading the data in. And that's kind of like a general rule for the Catalyst Optimizer. It kind of wants to filter the data as close to the source, as the data source, as possible. You also see this is not null portion, which is going to get rid of the null values. And that's kind of like an optimization technique as well. It wants to get rid of the null values kind of at the, as soon as it can. And that's added with the initial argument there. And then lastly, it's going to select the name and the age variable. So as you can see, the operations have been optimized and they've kind of moved around. And then there's the physical plan here at the end is going to show that optimized logical plan, but then it's also going to show how it's going to be ran on the cluster. And then this little star and one, that's kind of all three of these tasks are going to be ran in the first task there. It's a dummy example, so there's not a lot of resources needed for this. So that's kind of an example of working through the different stages of the execution plan. And if you want any more information on kind of the different example parameters, or explain parameters, sorry, you can go to this link and that'll be available at the end as well. I'm going to stop for questions. It doesn't look like we have any questions yet.
That is correct. No other questions.
All right. You guys are sleeping. That's okay. Okay, I'm going to move on. I'm going to kind of stay in this side-by-side view so we can kind of see the code and then the output as well. So finally, we're at the common transformations stage using a PySpark data frame. Kind of most of these transformations in this section are going to use these data frames that I created here, and kind of the data for these data frames is housed on kaggle.com. And it is a kind of a housing, you're trying to predict the house price of, these various houses in Ames, Iowa, using kind of these explanatory variables, these 79 variables. So it's kind of usually it's used for, students in college or whatever, but it's, I think it's a very good way to learn. And I brought those CSV files down and uploaded them to these different locations in the public data schema there. So kind of moving forward, let's start talking about some transformations. So this first one here, we're starting off with the basics. We're talking selecting the columns, and you're going to use this select function, and then you can, select your different columns, and kind of, as you guys know, kind of, taking taking only the columns you need is going to help that performance. And then this is going to just display the data frame there. Another kind of testing or performance tip is going to be subsetting those rows. So this gives you an example of limiting those data, like a data frame, to the 10 rows. And that's going to help with that testing performance and kind of testing your code so it runs quicker, when you're making the changes, kind of updating it. Then you can take that limit 10 out and run it on the full data frames. Another transformation you can do is sorting. So a PySpark sorting in PySpark, generally it uses the ascending order. So when we're looking at our data set here, it's using the sort function, and it sorts the sale price in ascending order. For you to do descending order, you can import the DESC, the DES function, and just hook that on outside the parentheses there. And then you can go ahead and display, or you can take a closer look using what we learned before, that select function, and select the price, so you can make sure you did it correctly.
Just sorry to do you mind if I chime in real quick, Colton?
No, go ahead.
I just wanted to call out that specifically, when we're talking about sorting, sorting is a very process intensive thing to be doing in Spark, and usually is not required, but there are occasions where you may need to sort to be able to run some particular functionality. And so we're demonstrating it here, but again, it's not necessary to sort your content at any time, and it is very process intensive, data processing intensive to perform. That's all.
Thank you, Dan. So moving on here, here's an example on how to remove duplicate observations. To remove duplicate observations, you use the drop dupes function. And for this example, we're deduping on the ID. I added in a couple QA checks into this example here. We're looking at if there were any dupes before, and then we used a dupe check kind of after dropping the duplicates. In this example, there weren't any duplicates, so they both show up as 0. Kind of moving on to joining data frames. So you'll use the join function, and you'll join. So this here joins the PySpark test or data frame with the PySpark sample submission data frame on the ID column, and then this is going to be a left join. And I added this little portion here to kind of understand what fields have been added. And basically what it does is it looks at kind of the columns in the original PySpark test data frame, and then it compares, and then if it's not in the original, then it'll print it out there. And I kind of like to use that when I'm joining data frames to kind of see what fields have been added to that original data frame. And in this case, the sales price field has been added to the original data frame. You can also append data frames. So this is an example of kind of appending the PySpark train data frame with the PySpark test data frame. We bring in the literal function because the PySpark test data frame does not have that sale price. And then the union by name function is going to stack those two data sets based on the column name there. And then a thing I like to do when I'm stacking data sets, I like to take kind of the row counts of each data frame. So I can kind of, keep track of how many records from this data frame came from, for the total combined PySpark data frame. So I take the counts of all three data frames there, and then I'm going to print the row counts here. This is an example of a multi-line or a formatted multi-line example here. You can use the kind of like the macro call. This is kind of the macro call here, and it's going to call these different counts that were created above. You could also do, 3 different print statements with the single formatted string there as well. The next thing we're going to look at is adding new columns. So we're looking for, apparently we're rich and we're looking for a large lot and a large living area when we're looking for a new house. So we're going to create a new column called large area living. We're going to import the call function so we can do the different column operations. We're going to also import the when function so we can do when this is true and this. We're going to create basically a binary flag for our large area living. And then I went ahead and, took those three columns so I can verify that our logic is correct. For this first one, 14,000 for the lot area. And then the living area is over 2,000. So yes, it looks like the logic was correctly assigned within our cell there. A way to rename columns is with this column rename function. And this is going to rename the year built to the year of construction. And this little QA piece here is going to check the data frame to make sure that that column is there, or that column, is not there. So in this instance, we want that column to be there, and our output says the year of construction. The year of construction is there. Yep.
Sorry to interrupt. We did get a question in the chat. I'll go ahead and read it out loud. Looks like it got answered, but I'll go ahead and read it out loud anyways. Does getting row counts, creating columns, lists, etc. trigger the task execution that display write function does? It looks like Dan responded saying, yes, it will, assuming Databricks hasn't cached a value in your output previously.
Yep. That's exactly right. There. Continue or okay. Yep. So the next example here is dropping columns, and we're going to use this drop function, and this is just going to be dropping the miscellaneous feature. I'm going to reuse this QA check I wrote above, which basically is going to check the data frame or the different columns of the data frame for this column. And if the column's there, then it's going to print that. If it's not, it's going to say it doesn't exist. Well, it dropped the feature, so we're expecting it to say it doesn't exist. And it does say that. Another transformation is filtering a data frame. So say we're looking for a house under 300,000. We would simply use the feature function and filter sales price for houses under 300,000. Say we want to use this for kind of the initial stage. Where that's our general price range, but we kind of want to get a look on the different houses that are actually available in all the neighborhoods. And we can pull the different relevant columns for our quote house search. Moving on to grouping and aggregating. So we're going to use the group by function to group, and then we'll use that average function to get the average. So what this does is it finds the average sale price for the neighborhood or for within the neighborhood. And then we're going to, let's say we don't like the regular floating point interpretation of the sale price in our output. We can go ahead and add that dollar formatting. So we're going to kind of select that neighborhood, and then we're going to select that sale price, and we'll give it an alias of the formatted sale price. And for these operations, we'll import the call functions, so we can look at so we can do different operations on the columns. And then we'll import this formatting string, so we can do this formatting here, which basically this formatting here is going to give it the dollar sign. This is going to show where the kind of where it's expected to start. The comma is going to show that we want it to be comma to include the commas in the dollar formatting. The .2f is going to show that we want it to be that 2 decimal places for the floating point there at the end. So that's how you would dollar format if you would want to do that. And then we can go ahead and display those results. Another thing you could do is you could replace values. So when I was looking at when we take a look at the neighborhoods here, it looks like some of them are truncated or kind of misspelled or whatever. We could go ahead and replace those different values with full names, or with whatever names you want. And the way you would do this, you would import the functions module. You would specify the column here, which in this case we want to specify the neighborhood column. And then this is going to be the when statement. So when the neighborhood is equal to North Ames, we want to actually say that it's North Ames instead of in Ames. Otherwise, it'll, just use the value. So you could go in and, fix all of these values if you want. And then kind of what I would do after I fix the value, I would go in and kind of get the distinct values of the different neighborhoods to check to see if we named it properly, and it looks like North Ames is right there. So the value was renamed properly from in Ames to North Ames. The last couple things here we're going to take a look at is dealing with missing values. So say you want to fill a missing value. You can, this portion of the code, it kind of creates the missing values data frame. And I did that because there weren't any missing values in the other data frames. So we're going to, so we create this data frame with missing values, and we're going to kind of fill those values here. And the way you're going to fill those values is with this NA fill function. And you will specify the different column names here and kind of what values you would want to fill the missing values with. So on the right-hand side here, we see the initial data frame that was created here with those missing values. And then you can see the filled values that I specified here. If the name's missing, I specified I want it to be unknown. Age or score, I want it to be 0, I guess. It kind of depends on the different case there. Moving down to dropping missing data. So this first portion is going to use the na.drop. This na.drop function is going to drop any rows with any missing values. So this is using this data set here. So every single one of these rows has a missing value. So it's going to drop all the rows. And as we see here, kind of for the bigger data frames that you can't really kind of visually inspect like you would here, I would recommend kind of comparing the different data frame row counts. So in the initial data frame, we have the 5 rows. After we drop the rows with any missing values, we have 0 rows. And then, if we try to display those, obviously there's no rows in that data frame because they're all dropped. You can also specify missing values or drop rows with missing values for different columns. So in this example, it's using the na.drop function again, but then it's specifying what columns you want to drop if there's a missing value in them. So we specify the age and score as being those column or those rows we want to drop if there's a missing value. And after we specify that, there's only that one left that has the missing value in the name column there. So that that concludes the common transformations for the PySpark portion. I made this little cheat sheet for you guys that gives all the operations and kind of how to do them for PySpark, PySpark Pandas, and Pandas Dataframes. As you can see, the PySpark Pandas and then the Pandas Dataframes, their syntax is going to be, really similar, if not the same in most cases. I'm going to go back to the standard view now. Let's see. So to conclude this office hours, we got a list of additional resources you guys can take a look into. This is going to be the link to the folder, kind of the general folder of the different office hour presentations, topic 1 through 4 there. These 3 are going to be the different data camps from the fall 2023 and then that spring 2024 focused on Python. This is going to be the Spark Definitive Guide. I've learned a lot from this guide, and if you're looking for kind of a resource on Spark, I would start there. There's a couple more Databricks resources, and then the last 2 there kind of gives more examples on using Spark for data analysis. So that concludes the material. Is there any questions?
So all questions have been answered in the chat, but we're receiving a few just now, so let me read them out loud. So Aaron is asking, is optimization a future topic?
Yeah, I think we'll take back that feedback, and hopefully we'll have at least some more information on the optimization within Spark.
And then we are going to submit a quick survey poll at the very end, so you can definitely put your queries in there of what you want to see next. We do have another question from Emil. General data related question. One way to transfer data from Databricks to Viya is to write the table to CDR and then use Viya %select_to_dataset to pull the table. This has been very slow for us. Another is to write Parquet files from Databricks to S3 and process those in Viya using CAS untested. Is there a recommended best practice for moving tables from Databricks to Viya to achieve the fastest overall performance?
Moving. What kind of?
Yeah. Are you talking about, Emil, are you talking about reading data from a database table into SAS? Are you asking, is there a faster way to get data from a database table into SAS?
Hey, Derek.
Yeah,
basically, yes. So
Yeah.
transferring any sort of data that we have in Databricks and ingest it into Viya for comparisons there as part of this transition, of course.
Yeah. So the issue is, like, even using that selected data set, it's going to ultimately push all of that SQL code to process on the SQL warehouse cluster. But then the issue you're running into that we have consistently ran into, and why we've had to create lots and lots of workarounds, ultimately is that ODBC driver. Because the data has to be read through that ODBC driver, and the ODBC does not allow for bulk uploads, and so it can be very slow when you're working with really large amounts of data. So that's why it's like there's really no perfect way right now to like read data into SAS that's like super large, that's going to be efficient because of that ODBC third-party driver. SAS used to have an actual Spark engine, much like we used to have the Hadoop engine before we got into Databricks, it's all proprietary, does a lot of stuff within SAS itself behind the scenes, but they removed it to be available for the SAS Viya 3.5 version we have, and it's only available on 4.0. So we're limited to that ODBC driver that we have to use to connect. And that's what's causing the slowness. Even if you were to write the data out as CSV, multiple CSV files, and you made some kind of a loop to iterate to import them, like if you're talking about lots of data, it's still going to take some time, right? Because it's just not ideal. So like what I would recommend is like instead of bringing that data back into SAS to compare, I would almost bring the data from SAS into Databricks and try and compare in Databricks, if that's at all possible.
Yeah, I mean, we're doing it both ways. I guess the team is just split up a bit differently. That's why just wondering if we can. Okay, so probably it shouldn't make a difference because both should be using ODBC, right? Whether it's written to S3 or whether SAS is used to pull it. So.
Well,
no, but
not necessarily. Only when SAS is pulling the data from a database table is it using an ODBC driver.
Can we? Sorry, I do want to just call out that the purpose of this office hour is primarily about this the Spark data framework that we're doing with Python writing, and so like not to discredit the question, and I'm not trying to ignore the question. I'm just thinking, can we take that offline?
Yeah.
As we've also had a couple of other discussions about this as well, but I do want to highlight the fact that there's room for this conversation in other environments, in the CCSQ chat, analytics chat as well, channel. And
No, that's a
if
good
there were
call.
if there were any specific questions regarding this topic that Colton has prepared for us, and then also we have the survey at the end.
Yeah,
I do want. Sorry, Emil, I do want us to get to your question, and I don't want to like cut. But I am also trying to,
Yeah, no problem. It's fine.
Yeah.
Mm-hmm.
Yep.
Thank you, Dan. We do have a few more questions, but I'm wondering maybe we can answer them later, post them on the portal just for the sake of time, if that's okay with everyone. And I'll go ahead and present the survey. So let me find it. All right. Please take it on your way out, and any feedback that you want to give our developers or any topics that you'd like to see in the future, please use this poll to discuss that. Thank you. All right, just 20 more seconds and I'll end the poll. And if you're still on, just reiterating what Dan said, feel free to reach out to the CCSQ Data and Analytics Slack channel for further communication, and you can post your queries there and have that conversation then. All right, thank you everyone and have a great day.
Thank you. Great job.